you. So last time I'd started to tell you about the rigorous results on critical long-range percolation. And as I mentioned, I'm going to state the results kind of in a historical order. So we'll build up from weaker to stronger theorems. And these results are going to concern both long-range percolation on ZD. So just as a quick reminder, we consider percolation where any 2 points on ZD can be connected by an edge, and the probability that the edge between x and y is this. It's 1 minus e to the minus beta times the distance to minus d minus alpha, which of course when the points are far away from each other is approximately just this. Okay, and beta c is the point of phase transition, which is less than infinity when d is at least 2 or d equals 1, alpha less than or equal to 1. Okay. And the theorem that I just stated when we ended last time is that for the hierarchical lattice, or I should say that for hierarchical, we have beta c is finite if and only if alpha is strictly less than d. Okay? And again, for the hierarchical lattice, the dimension is kind of fake in that you can always transform to the one-dimensional case while keeping the model sort of equivalent. Okay. Good. Okay, so the theorem I stated last time that was in the hierarchical lattice, alpha less than d, and alpha is always positive. We have the critical 2-point function is given up to constants by this minus d plus alpha, okay? Which you should think of as being the same scaling as the Green's function for the random walk on the hierarchical lattice with jump kernel proportional to this, okay? So in particular, in the hierarchical lattice, you do not have this transition between long-range and short-range behavior, even for the random walk. You can think that the hierarchical lattice just doesn't have short-range effects in it. Again, because if you look at two boxes, every point in this box is far away from every point in the neighboring box when the boxes are large. Okay, there really is sort of no boundary terms. Okay, so the Green's function for the random walk does not have this transition. You just always have this minus d plus alpha scaling, even when alpha is large. And what this theorem says is that the critical percolation 2-point function on the hierarchical lattice always behaves like the Green's function. Okay, and we should stress that this is this holds even in the regime where the model is not mean field, right? So we'll still have that the mean field if and only if d is at least 3 alpha. Okay, so in fact, it's actually a corollary of this that the triangle is finite if and only if d is bigger than 3 alpha. Okay, so in particular, triangle condition being finite, as we discussed last week, is a sufficient condition for mean field critical behavior. You can just check that it converges exactly under these things. It's just a calculus exercise. Okay. In fact, we can also prove that the exponents don't take their mean field values when d is strictly smaller than 3 alpha as a consequence of these rigorous hyperscaling inequalities I mentioned before, but I won't state that for now because we're going to state much stronger theorems soon. Okay. Another thing here is that in the case where d is equal to 3 alpha, you can deduce from this that, with a bit of work, that you get this logarithmic divergence of the triangle as you approach B to C. And in fact, the proof that I showed you on Friday that the triangle condition implies mean field behavior, I actually only showed you that when the open triangle is less than 1. Okay, and the classical way of extending that to the case where the triangle is just finite is actually very quantitatively poor in the case where the triangle is large, basically because you look at some open triangle with a large opening, you prove your estimates there, and then you force some edges, you do some surgery to the configuration to make an actual pivotal edge. And this surgery is extremely expensive. But in fact, a few years ago, I found a different proof that the triangle condition implies mean field behavior, which is much better quantitatively. And in particular, it says if you have logarithmic divergence of the triangle, then the critical exponents take their mean field values up to logs. It doesn't usually give you the correct power of log. So in this case, if you have this just log to the 1 blow up of the triangle, you get a log squared upper bound on, for example, the susceptibility will be at most 1 over epsilon times log squared. Okay. But at least it does tell you straight away that you have this mean field behavior up to logs, even if you don't get the right log. Good, so I'm hopefully going to give you the full proof of this, but first let's continue going through the other results. Okay, so this result is about hierarchical, but a few years, or just 1 or 2 years later, I was able to extend this to ZD in a weak sense. So, of course, this is not always true. You know, we have this SAC prediction that basically this minus d plus alpha scaling occurs in the long edge relevant regime, but then it ceases to be true in the short range, effectively short range regime. And we also know that this transition between these two, it's going to be very hard to understand where it occurs. So if we want to prove theorems, we probably need to prove theorems that somehow circumvent this issue of not being able to understand where the transition occurs. So the first theorem I proved, in fact, is just an upper bound. So on ZD, alpha less than d. Again, although, again, the bound about state is vacuously true in the case alpha is greater than or equal to d as well. What we get is a spatially averaged bound. So if you sum the critical two-point function over a box, if you average it over a box of radius r, then it always satisfies up to constants this bound as an upper bound. Okay, so you can think, what is this? It's just saying this line is always an upper bound on the exponent, which of course is consistent with the conjecture, and it should be sharp up until you reach this transition to not really being long edge relevant anymore. Okay, now one interesting thing about this theorem is the proof really, so it doesn't use the theorem from the hierarchical case, but it uses very strongly hierarchical methods. So we'll see that basically the way you prove this is by a kind of comparison to the hierarchical model. And of course, that when you do such a comparison, it's not really going to be stochastic domination or anything like that, and you always have the problem that the critical values are different, right? So you're not going to be able to compare them nicely like that. But it really does use, in some more generalized sense, a comparison to the hierarchical case, and I'll hopefully be able to tell you about that in detail. Okay, good. So, when I wrote this paper, I had a section at the end with some problems, and I mentioned, well, one problem that I wrote there, which we still can't solve, is can you improve this to a pointwise bound? Okay, and actually one thing that's really annoying is that you would like to deduce from this that the triangle condition holds when D is bigger than 3 alpha, but actually there's too much spatial averaging, and you can't, as far as I know, after spending a lot of time trying, you cannot deduce the finiteness of the triangle from this bound. So one problem is, can you prove a pointwise version of this upper bound? Or another useful thing would be a Fourier transform version. That would also be sufficient to get control of the triangle. But one of the other problems that I said, of course, it's very natural, give conditions under which there's a matching lower bound. And in fact, it only took a month or something after I posted my paper. Johannes Baumler and Noam Berger, so Johannes at the time was a student of Noam's in Munich, and he's now a postdoc at UCLA. So they showed that if you look at the same quantity, then, well, if alpha is less than 1, then you get a matching lower bound, again with some implicit constants here. Okay, if alpha is equal to 1, they get a lower bound that's matching up to a log factor, 1 over log. And when alpha is bigger than 1, the power just sticks at 1. Okay, so what you can think...
It's 1 over RD, I guess, right? Yeah, it's 1 over R to the power G.
Oh, yeah, sorry. Thanks. Okay, so you can think that basically their theorem gives you a lower bound like this, where this is 1. Okay? So, in particular, this completely solves the SAC prediction for alpha less than 1. Okay, at least at this with this spatially averaging business. Okay, so for D equals 1, this is the only regime where you have a phase transition, so it completely solves this SAC prediction in the one-dimensional case. Okay, in the two-dimensional case, it covers this regime between 2/3 and 1 where the model is not min-filled. Okay, so, you know, even in 2D, and again, there's not so much difference anymore between 1 and 2 dimensions, say, when you're looking at long-range models. But even in 2D, we get this regime between 2/3 and 1. It's not min-filled, but we can verify the conjecture. Okay, and last year, I showed that under this same assumption, and using one of the key ideas that they had in this Baumler-Berger paper, this is ZD again. This is ZD2. Under the same assumption that alpha is less than 1, we can now improve this to a pointwise bound. Okay. But the upper bound should always be true pointwise, but we still don't know how to do that. Okay.
Sex predictions for both eta and the delta that are confirmed?
No, only for eta for now, but let me get to that. Yeah, this is just for eta. So there's a hyperscaling inequality relating that this is one of actually the key contributions of the earlier work that I mentioned last time on, that was the first work I had proving some power law estimates, but not the sharp ones. 2 minus eta is less than, hopefully I'll get this right, delta minus 1 over delta plus 1 times d. And so once you know the conjecture for eta, you get a one-sided bound at least on delta, but the other side is harder. Okay. Good. Okay. So, one thing about these results on the two-point function, again, is that, on this curve, there's this other point that's supposed to be interesting, and whether it's to the right or left of 1 depends on what dimension you are, which is d over 3, right, which is when you should change between having mean field or behavior or not. And, these results, they just don't see this at all. And in some sense, the method, which I'll show you, it just is not capable of distinguishing between these different regimes. It never uses anything that would distinguish between the different regimes. So somehow, if you want to prove things about other aspects of the model, like the volume tail, you have to do something else. And so I first did this in the hierarchical case. In fact, I think this was what I gave a seminar talk on last time I was in Orsay. In fact, these lectures so far have been a sort of 6 or 7 hour version of that talk I gave here last time, which is that, again, on hierarchical, that if you look at the volume tail, so remember K is the cluster at the origin, then up to constants, well, it's n to the minus a half in the high dimensional regime, n to the minus d minus alpha over d plus alpha, which is this conjectured curve here. Well, this is d plus alpha over d minus alpha, and that's because delta is defined to be the reciprocal at the exponent here. And in the critical dimension, any guess on the power of the log? Anyone? Yeah, no, it's hard to guess where these things come from. It's log to the 1/4. Okay. Now, one interesting thing I would point out there is that this log to the 1/4 is not the same that's predicted to hold for nearest neighbor percolation on Z6. That's 2/7. 1/4 and 2/7 are very close to each other. Now, I don't think you should take that as evidence that these predictions are wrong. It's just saying something about these models just genuinely behaving a bit differently than the nearest neighbor models at the critical dimension. Okay. On the other hand, what we'll see is that, going back to this phase diagram for the long-range models on ZD. Sorry, that was supposed to be D, right? In this model, you have these two different parts of the critical dimensional curve. This one where you should behave like nearest neighbor percolation on Z6, and this one where you're long-range effective. And actually, on this line, we do expect the Euclidean and hierarchical models to behave the same. So I'll come back to that. So, it's just that there's just different logarithmic corrections on this line and on this line. Okay. So it's not that the hierarchical model is just always irreparably different than the Euclidean. Okay. Now, the proof of this, basically it introduces a way of doing a renormalization group type analysis for percolation. And it tells you a lot more than just this volume tail thing. It actually gives you, particularly in the high dimensional and critical dimensional regime, it gives you very, very precise results about the model, including scaling limits and so on. And in all three cases, it verifies this basic picture of hyperscaling versus mean field in terms of, what the geometry looks like. So you get this basic thing that if you say how many big clusters in the scale on some size r. And how big are they? Then you get this dichotomy between the low-dimensional, high-dimensional cases that we were discussing in our non-rigorous overview, which is that in low dimensions, you get order 1 big clusters that have size r to the d plus alpha over 2. Okay, and we'll see interpretations for this number when we do the proof. In the case d bigger than 3 alpha, we have order r to the d minus 3 alpha, so some power number of these large clusters, and they have size r to the 2 alpha. Okay, so in particular, once you get into the high dimensional regime, the size of these clusters stops growing with the dimension, and that's of course very similar to what happens in the nearest neighbor model, right? That these high dimensional clusters are 4-dimensional objects. They have this size R4, and of course that corresponds to taking alpha equals 2 here. Yeah, that's how it is. And in the critical dimension, we get that there are order log r, large clusters, that's log to the 1, if you like. And what is their size? Well, it's smaller than this r over 2 alpha by a factor square root log r. Okay, so this is not quite a precise statement, but you can think of this as saying that if you want to compute something, like a moment of a cluster or something like that, you'll get the same answer as if you just look at the contribution, say, okay, let's say I want to look at the third moment of the cluster at the origin inside the box, for example. Then you should say, okay, it's basically the same as if in the box there were just this many clusters of this size, and then it's just, the probability of the origin belongs to one of these clusters is the number times the size divided by the volume of the box, and you'll get the correct estimate for the moment. Okay. And of course, again, the relationship between this exponent and the two-point function exponent can be thought of as a hyperscaling relation. Okay. Good. So that's how things stand, I guess, in terms of things that are actually available in the archive. So now let me tell you the new results that I also want to tell you about. And essentially, what I've been working on for the last year or so is trying to extend this hierarchical analysis to ZD. And a corollary of that is I now understand everything that's going on here much better, and I think if I went back to write this paper now, I would do things quite differently. So as a result, I won't really tell you anything about the proof of this. I'll just tell you about the proof on ZD. And in some ways it's much nicer because I know what I'm doing more. There are aspects of it that are much more technically difficult, but those are things I'm mostly going to not tell you about. Okay.
So ZD, the answer there should be this alpha C, this third stage.
Yes, so I'm not going to have any results about that regime.
There's no way to have something like that for the hierarchical.
Yeah, you don't have the transition to short-range behavior yet.
There's no limit of it that would...
I don't think so. I think you should really think again that you have this transition here between hierarchical-like behavior to nearest neighbor-like behavior, and in those you can't get long-range effects in the nearest neighbor, and you can't get hierarchical short-range effects in the hierarchical. Okay. Good. Okay, so basically, I'm not going to tell you anything about this regime. Actually, you know, in some ways I have, because this line alpha equals d actually does include points in this regime, and we know, for example, that you have a continuous phase transition with some power law bounds. We can't compute the exponents exactly, but you know, we do have some bounds that treat models in this effectively short-range regime. But I'm not going to say anything more about that now. So we're going to restrict attention basically to the three other regimes. Okay, so including, you know, again, this is the long-range high-dimensional, short-range high-dimensional, long-range low-dimensional. This is short-range low-dimensional. And then, of course, we have these lines with the extra complications, log factors, and so on in between them. Okay, so this would be like the high-dimensional but marginally short-range. This is long-range and marginally high-dimensional, or marginally low-dimensional, depending on how you think of it. I guess marginally high-dimensional is the better way to put it. Okay, so I'm going to start. I'm going to state not the full theorems for now, but we'll come back to saying more later. So I'll start with the theorem about the high-dimensional case. Okay, so let's suppose that D is bigger than 3 alpha. So this is going to correspond to everything under this line, which you can see applies to the whole long-range high-dimensional regime and part of the short-range high-dimensional regime. Okay, then the first thing is that if you look at the volume tail, it's actually asymptotic to some constant times 1 over root n. Okay, and in fact, you know, this is something I didn't really understand how to do when I wrote this hierarchical paper. I guess I wasn't thinking too much about it. Here I really wanted to get into scaling limits, and these things about identifying precise first-order asymptotics was much more important, but actually you can go back and improve the D bigger than 3 alpha and D equals 3 alpha in the hierarchical case to give you precise first-order estimates with constants if you want. So this is the first thing. The second thing is that you get scaling limits. Okay, so as measures. So if you look at the cluster of the origin, and you look at the sum of all these counting measures where you scale everything, then this converges the law of this. So actually it turns out the best way to think about scaling limits at this kind of thing is to not use probability measures. I'm sorry, I need to include some scaling factor here. This is 1 over r to the 2 alpha. Wait, hang on, sorry. Let me just say there's some scaling factor I can put here. And some factor I can scale the probability by, so that this converges to what's called the canonical measure of integrated superprocess excursion. So I won't say too much about what this is. I may say more later, but basically this is the same thing. This is the same scaling limit as the branching random walk. Okay, that's perhaps the best way to understand this.
These Brownian integrated super excursion?
It's sometimes Brownian, it's sometimes Levy.
Oh, okay. That's
Yeah.
what you say.
Yeah, right. So it's Brownian if alpha is bigger than 2 with logs when alpha is equal to, in that you have to put some additional log scaling to get it to come out right, and it's Levy when alpha is less than 2. Okay? So it's an interesting thing, even though this method is kind of a very long-range thing, it does still apply, at least sometimes, in the regime where, in fact, you're effectively short-range. Okay? And you can think about this condition d bigger than 3 alpha as meaning, when you look at the condition for having high-dimensional critical behavior, it's that it's either d is bigger than 6 or d is bigger than 3 alpha. Okay? And you can think about this condition d being bigger than 3 alpha is saying your mean field because the kernel is heavy-tailed enough, even without needing to know what the dimension is, right? So, of course, you can be mean filled for sort of more than one reason in this regime here, but this d bigger than 3 alpha is enough for our analysis to work.
Because you said it's short range, but you still see Levy.
You get the Brownian. The transition to short range is at alpha equals 2.
And where is it on this picture?
So the theorem applies whenever you're below this line, right? But in this cone here, you're effectively short range, but the theorem still applies and you get Brownian.
And below it's Levy.
Yeah.
Okay, good.
Right, so this is exactly this transition between long and short range behavior, okay? So this is the condition under which these things work from scratch. And again, maybe you could prove similar results to this with the lace expansion, but the key point here is that this is non-perturbative. So, the lace expansion always had these caveats that, you don't get to work with your favorite kernel. You have to say, maybe it turns out this is your favorite kernel, but you have to work with one of these spread out ones, right? Like you need some numerical assumptions about the model besides just the fact that it's high dimensional. Like, we can't do nearest neighbor percolation just in more than 6 dimensions, whereas, okay, this doesn't treat all the different regimes where you get mean field behavior, but it treats the whole effectively long range one and part of the short range one via just like a strict inequality. There's no plus 100 or something on the right hand side, if you like. Okay. Good. Okay. So, and moreover, we can compute what these things are and these scaling factors. Again, so we're just rescaling a probability measure here. So the thing you get on the right is not a probability measure. But if you want to extract a more standard limit statement in terms of probability measures converging to probability measures, you just put in some conditioning. Here, you condition on being in a large cluster. Okay. And these scaling factors here will also see the transition between these alpha bigger than 2 and alpha smaller than 2 regimes, in that this zeta r you should think of as this typical size of clusters at scale r. So it's going to be r to the 2 alpha if alpha is less than 2, which is the same as in the hierarchical case. And it should be r to the 4 if alpha is bigger than 2, and there's a log correction when you're at alpha equals 2. For some reason, I didn't write down what zeta r is in my notes, so I'm at risk of making a mistake here, but that should be right. I mean, it should just be, how big are these large clusters on this scale r? Okay. And whereas eta r will denote the probability that you belong to one of these large clusters. Okay. Good. Okay, so that's the result above the critical dimension. Oh, actually, sorry, before I move on.
This is the plus means it's just.
Yeah, this means it's very close to being finished, though. I mean, I really wanted to have it online.
It is perturbative. It's 25 plus.
Right. Yeah. Plus epsilon. Yeah. No, I very much hope that it will be on the archive certainly by the end of this year. hopefully much sooner than that.
Yeah, we're working like dogs to prove that for the usual percolation, the limit will be the what we call the Brownian motion on this thing.
Right, yeah.
Now you're saying there is something more to do for the long range thing. It should be the same limit, right?
Yes.
And your method is even better because it's non-perturbative.
Yeah, but only for long range. Although, yeah, but here's my addendum to this.
No, but I mean, if we can't do it, then we could just.
Yeah, you can use the long range thing. Although in the short range case, as I said, me and Arto also have some scaling results. Although it seems like there's a lot of competition for getting these online. So maybe we should discuss that afterwards.
Don't worry. Our rhythm is.
Okay. So this result I stated under this non-perturbative assumption, but in fact, if you happen to know something about the two-point function, then you can get it to work in the whole high-dimensional regime. So the condition is that d is strictly bigger than 3 alpha, or d is bigger than 6 and the two-point function satisfies a bound of this form, which we know that it does for spread out models by the Lace expansion, or d equals 6, alpha equals 2, and you get this version with the log. In fact, in both cases, you don't really need a bound as tight as this. You know, it would suffice to have slightly the wrong power here or the wrong power of log here. But you know, these are the actual bounds that hold, and these are known to hold under the conditions where you can get the Lace expansion to work. So in other words, you know, the method works from scratch in this regime where the kernel is heavy-tailed enough, but in the remaining high-dimensional regime, if you happen to know something via the Lace expansion, for example, you can improve that to much more precise results about scaling limits and so on. And one of the curious things about this is this conditional part, you know, it works no matter how large alpha is. And in fact, I think, although I haven't written this down carefully, it should work for any non-compactly supported kernel in more than 6 dimensions. So on the other hand, it definitely doesn't work for short range, for actually finitely supported kernels. You know, there are some tricks you can do in the long range world which are just not available. I mean, our whole analysis just doesn't make sense for the short range model. So it's something very curious going on here that needs to be investigated more. Okay.
In the assumption, it's beta C, right?
Oh yeah, sorry. Yep. Okay. Good. So yeah, to summarize, this result applies to the whole high-dimensional regime, but non-perturbatively only under this line, and perturbatively using the inputs of the Lace expansion in the whole rest of the regime. Okay. Okay. So the next result is going to be about the behavior on this line. So this is where you are long range, you're really long range, but you're at the critical dimension. Okay, and again, all the results in this case are going to be non-perturbative. So the first is that, again, there exists some positive constant A such that the volume tail is given exactly like in the hierarchical case. It's larger than the mean field scaling by a log to the 1/4. Okay? And the other thing is that you get the same super Levy scaling limits. where, again, these scaling functions have log factors. And again, this scaling function, zeta r, for example, it's describing the typical size of a large cluster on scale r. So in the high dimensional case, it was r to the 2 alpha. And here it's going to be smaller by a square root log factor. So it's of this order anyway. Okay, so, okay. So let me make a few remarks on this. So again, I'll give you an overview later of more about the proof methods. And the big picture idea is to implement some version of the renormalization group type analysis for percolation, and specifically for long-range percolation. And I think one of the really nice things about these works is that for these long-range models, it turns out that there is a really elegant way of doing the renormalization group, which is much more probabilistic, and I would argue less technical than the traditional ways of doing renormalization group analysis for like the 5-4 model, for example. The big downside of this method is that it only works for long-range models, which is, of course, quite a serious drawback. But I'll say more about that later. One interesting remark about this is you have to prove the scaling limit result first, and then you compute the logs. And basically, this is something that comes up over and over again in this method. Basically, what you show is that you can define these functions, the scaling functions, that are just some regularly varying functions of the appropriate index, and you show that if you scale by them, that you get the right limit, and then you actually use your knowledge of the scaling limit to help you compute the log corrections. Okay, and we'll come back to that in more detail later. Okay, good. And I should say again, all these things. Here I'm just writing down a couple of the outputs of this analysis, but it tells you a lot more. For example, it verifies again this story I had on the board here that I erased about, the geometry of these clusters on a given scale, how many large ones there are, how many there are, the fact that this really describes accurately the model in the sense that if you want to compute moments, you'll get the same answer as if you just do this sort of counting problem. Okay. Good. All right, so, and maybe I should say another consequence in both of these cases is that we also get this spatially averaged version of the SAC conjecture, which is that the average two-point function in the high-dimensional case will have this minus d plus alpha scaling when alpha is less than 2, the minus d plus 2 over the log when alpha is bigger than 2, and when alpha is equal to 2, and the normal Brownian Green's function scaling when alpha is strictly larger than 2. Okay, and this is really just a consequence of the theorem about the scaling limits in some sense. I mean, I guess it's maybe slightly stronger because this is just weak convergence and there's something about a moment. But okay. Of course, in some of these cases, we're sort of assuming an upper bound of that form, so it's less interesting. But again, this regime d bigger than 3 alpha does include actually this whole line of where you're marginally short range except for this one point. And it also includes, this cone of this region where you are effectively short range, not marginally. Okay, and in this case, when you're here, you get the correct scaling again in the spatially averaged sense as predicted by SAC. Okay. So, of course, it remains to tell you something about the low-dimensional regime. Maybe I'll. What's the stick? What's that? On the table. Oh no, I was looking for the stick to bring the board down, but. Ah yes. So,
Is it possible to lift a bit the blackboard behind?
yeah, maybe I'll this one up there. This one. So, I'm not sure that helpful. Yeah. Okay. So actually, before I tell you about the long-range thing, let me give you another aspect of these high-dimensional things, which is going to inform our short-range discussion. So, one of the other quantities that we can compute in the high-dimensional and critical dimensional cases is something called the radius of gyration, which is one of the precise versions of the correlation length, but it's going to be not the usual way that we do things, but in terms of cutting off long edges from the model. And in fact, maybe I'll just say something about this, because this is the whole method that underlies all these approaches. But it's going to be important to understand the method to some extent in order to state the short-range results correctly. Okay, so the main idea behind the whole analysis is, again, it's going to be a kind of renormalization group method. Okay, now the traditional way of doing renormalization group is, first of all, you work with these models, like I said, that you have a Gaussian field plus some kind of weak interaction, and you try to understand the effect of having that interaction on this Gaussian field. And the Gaussian field is usually a Gaussian free field, right? So this is so let me say that this is not the idea. This is the classical way of doing things. So you start with the GFF, right, which is the Gaussian field, which in the short-range case has Green's function correlations. Plus some kind of interaction. In other words, you weight this measure by something, maybe depending on some local observables. Okay, and you try to understand what this interaction does at some appropriate critical point. Okay, and the traditional way of doing the renormalization group, which I guess in some form goes back to the original work of Wilson, but I'll talk more about the more recent, the rigorous math versions of this. I'm thinking in particular of the work of Bauer-Schmidt, Bridges, and Slade. So what they do is they say, okay, let's replace the Green's function or let's say rather than replace, you want to cut off the Green's function. So you want to replace it with some finitely supported thing, and that gives you, that will mean that your Gaussian field with those covariances is now finitely dependent. Points sufficiently far away from each other are exactly independent. Okay. Now there are many ways that you could do this, and the precise choice of how to do this is a big part of the art of doing these kind of arguments. Okay. So and you get some scale r. And then what you want to do is understand how do quantities depend on r. Okay, so usually, you want to either, actually it's usually much nicer if you can to vary r continuously and try to get some approximate differential equations that are satisfied as you vary this thing. For technical reasons, they often work with discrete steps, which is less nice computationally, but it can be easier to prove things about. And then eventually you want to use all your understanding of how these quantities depend on r to say something about the critical behavior of the model. Okay. Now, the big downside of this approach, at least in all the instances that I'm aware of, is these intermediate models you get. So for example, you start with the phi-4 model, and then you replace the GFF with this finitely supported GFF. These models, finitely dependent GFF rather, these intermediate models are just horrible. They have no properties, essentially. And that's not necessarily a bad thing, because actually often the original models they want to study don't really have any properties anyway. So the phi-4 model does have many nice properties, and you can use probabilistic arguments about it. But if, for example, you're working with the Heisenberg model, which is where you have three-dimensional spins, then this has very few correlation inequalities or other probabilistic properties. So it's not such a bad price to pay by moving to these funny intermediate models. But the downside of that is that because you essentially only have analytic tools available to you, these tend to be perturbative. So the way they'll work usually is you say, okay, imagine my interaction that I've added is very, very weak, and so I'm very close to being exactly Gaussian, and then I want to show that I remain Gaussian, as I remove this cutoff, and that I want to track various quantities describing how far away from Gaussian I am, some variances and things like that. Okay, and the methods, the upside of this kind of way of doing things is that they're very robust, in that these weak interactions that you add can be highly arbitrary, because you don't really care about what properties they have, as long as you're close enough to Gaussian in some appropriate, extremely complicated sense involving often these norms with like 10 parameters and things like that. Okay, but in particular, they can handle some very complicated models. Like there are papers, for example, on self-avoiding walk with attraction between, like you like being next to a site that you visited before. So these have a mixture of repulsion and attraction that would be very difficult to treat using more probabilistic methods. Okay. So what is the new idea? Well, basically the point is that for long-range models, we can do our cutoff with the kernel rather than with the Green's function. So you can think this is like these two approaches are sort of dual to each other. And I should say this is not really how I came up with these things. It's after I got everything working, I was able to understand, okay, what is actually the relationship between what I'm doing and the more traditional approach. But you can think they're kind of dual to each other in that in this traditional approach, you're truncating the inverse Laplacian, right, the Green's function. And in my approach, you're truncating the Laplacian itself, which is like I minus j. Okay, so what we're going to do, okay, so remember the kernel we're always going to assume is a function of the distance, which can be an arbitrary norm. And in fact, in the paper, I considered a more universal class of kernels where you're allowed to have some errors and so on, but let's just say it's this exact distance kernel, okay? And I'm going to write this, okay, up to changing some constants in the form integrating a power one smaller, okay? And what I'll do is I'll define the cutoff kernel, JR. I guess I should call this something else. JR of t by just truncating the integral at R. So you can think this is a bit like just removing edges longer than R from the model, but it's better behaved analytically than that. I'm also changing the kernel at all smaller scales as well. Okay. And essentially, what's underlying these results is that really we do all our analysis by saying, okay, I now have this two-parameter model, right? I have beta and I have this cutoff, R, okay? And what we're going to do is we're going to almost always fix beta to be beta C, where that means beta C for the original kernel with no cutoff, okay? And we want to understand, you know, how, if I have some observable of the cluster at the origin, what is this asymptotic, like what are the asymptotics of this as R goes to infinity? Okay? And basically all of these results that I just mentioned, these are the new ones rather, the ones that are not on the archive yet, they are all based on some kind of asymptotic analysis of moments as a function of the cutoff, like this. Okay? So, you know, when you eventually want to go and get results like this, in fact, both of these are stated without any reference to cutoff, right? But, you know, the way you do things is you understand all the moments. For example, if you want to understand the volume tail, the way you do it is you first understand all the moments as a function of the cutoff, and then you have to do some Tauberian theory, messing around with some, you know, that kind of thing, and you can extract these volume tail asymptotics from them. Okay, so in fact, for example, in this high-dimensional case, really the way these volume tail things are proven, for example, is you show that if you look at the piece moment of the cluster at the origin as a function of the spatial cutoff, that it satisfies a first-order asymptotic estimate where we first get this combinatorial term, 2p minus 3 double factorial. Actually, this should be familiar from the tree graph inequality. This is counting the number of leaf-labeled binary trees with p leaves, times some constant, which is not the same as this constant. In fact, I think this constant a is I think it's a is 1 over pi a, or something like this. This is something that comes from the Tauberian analysis. Although I may have forgotten some factor of 2 there. So. To the power p minus 1 times r to the times this constant alpha over beta c times r to the alpha plus p minus 1 to alpha. Okay, so you can think this basic form of these asymptotics is again related to all these basic scaling theory kind of ansatz formulas that we were talking about on Friday. Okay, and again, this is somehow for the volume tail. This is really the main theorem, if you like, and then you can extract the volume tail as a corollary of this via some Tauberian theory. Yeah.
Just to be very sure, when you speak of beta C, it's not beta C of...
It's not beta C of R. Yeah, it's beta C of the original model. So, yeah. So, yeah, I'll say more about this at some point, but somehow in the traditional approach to nearest neighbor percolation, you know, one way you could do things is to say, send beta to beta C or p to pc from the subcritical side and try again to do something similar to this, to understand asymptotics of moments. But when you do that, it's much more complicated, and it turns out this way of doing things with this cutoff of long edges is analytically much, much better. And you can think in the case of the high-dimensional case that essentially when you get some errors to the mean field behavior, they're in terms of triangle diagrams, which are very open. So, you know, in the nearest neighbor case, you got these triangles with this like unit, opening with one of the vertices of the triangle being at really two different neighboring things. Here you're going to get triangles that are like open up to scale r, so they're actually converging to 0. That's not really how the proof, it actually is how the proof works in these two cases. It's not how the proof works in this case. But you can see that something analytically much nicer is happening, because essentially these errors to mean field scaling of the derivatives are going to 0. And in terms of these scaling limits with the spatial structure and the embedding and so on, the way things work is you do something very similar, but you look at moments that, quantities that involve the embedding. So for example, you could look at the sum of x in the cluster at the origin of, you know, the inner product of x with some vector, for example, right? And then you establish a similar asymptotic for this. And if you do this for not just these things, but, you know, you put powers here and you have more than one point and more than one vector and so on. If you do this for arbitrary quantities like this, then that, well, it tells you something about the scaling limit of these models with the cutoff. And then again, you have to do some Tauberian-like analysis to get things about the model without cutoff. And the story is very similar in the critical dimension. Except that you're going to get some logs everywhere, right? And in fact, there's something very nice that happens in these moment asymptotics, which is that for just looking at the volume, all the complicated stuff where you potentially have logarithms and so on, it only enters at the second moment and then just propagates in a simple way. So in fact, when you do a similar analysis in the case of the critical dimension, and you look at the pth moment, or the formula I'm about to write down holds both at and above the critical dimension. So you get this relationship where you can express all the higher moments just in terms of the first two, to first order. And then there's this alpha over beta c r to the alpha. This is actually just equal to the asymptotics at the first moment. Okay? So, you know, again, we'll see more about where this comes from later. But you should think again that basically whatever complicated things with logs that are happening, they only happen in the second moment, and then everything else they just propagate in this simple way. Okay? And this, by the way, is very strongly related to what I was saying about how we first compute scaling limits and then compute the logs. Because in fact, you can already see a scaling limit coming out of this, which is that if you look at the cluster at the origin, you look at the size biased measure, so you weight by size of k over its expectation, and then you normalize that to have mean 1. This says that it converges to a chi-squared random variable, right? That's what these, in some sense, that's why these constant coefficients are very important, because they're actually telling you what the scaling limit is, right? In this case, the double factorials are the moments of the chi-squared, and that's why you get a chi-squared limit. Which, by the way, is the same thing you get if you take a slightly subcritical branching process. You do the same thing of size biasing and rescaling. It will have total mass converging to a chi-squared random variable. Okay. Good. Okay. So, all right. Let me use this book. So as I was saying, in order to prove these things about scaling limits, everything works by computing the first order asymptotics at these moments, possibly with some spatial weighting. Okay? And one of these moments that we compute is something called the radius of gyration. Right, this is going to be a function of this cutoff. Okay, and it's defined to be you sum over the cluster of the squared Euclidean norm. This turns out to just be much more algebraically convenient. Our model is defined with respect to an arbitrary norm, but we'll do these moments with respect to the Euclidean norm. Divided by the size of the cluster, square root. Okay? Or equivalently, if E hat, and these are all beta CR, right? Equivalently, it's the square root of the expectation under the size bias measure of, I was going to draw a large X, but this one's quite large, or this is a uppercase X, where big X is a uniform element of K. Okay, so if I sample K according to the size bias measure, pick a uniform point, look at its squared Euclidean norm, take the expectation of that under the size bias measure, take the square root. So in other words, you can think that this radius of gyration is saying how far away is a typical point at the cluster under the size bias measure. So, you know, I was often talking about these typical large clusters and saying, you know, how big is a typical large cluster and so on. So really the way you should understand that is via this size bias measure. At least that's a very good way of understanding things in this cutoff world. Okay. So
what is it called, gyration? There's nothing turning?
Yeah, that's a good question. I didn't come up with this terminology, and
It's Greenwich lemma, right? If you sum the distance squared, it's the in high school.
It's something to do with angular momentum or rotational inertia or something. Yeah. Yeah. Okay.
High school is way back.
Right. Okay. So this is one of the quantities that we can analyze using our method. Okay. And what you see in this setting, in the high dimensional setting, including at the critical dimension, is that this is asymptotic to some constant times. I'll just keep writing A for some constant. It won't be the same constant. Well, in the case alpha less than 2, it's just going to scale like R. Okay? And what you can think this is saying is that in the long-range effective regime, when you apply the cutoff at scale R, the model feels it on scale R. You know, the clusters, they find it difficult to get to a distance further than R, i.e. the scale at which you applied the cutoff. Okay? Now, if alpha is bigger than 2, it will be R to the alpha over 2. Okay? So what this is saying is in the short range effective regime, you know, you apply this cutoff at scale R, you're truncating all edges longer than R as well as slightly decreasing the weights of the ones shorter than that. But actually the cluster doesn't feel this on that same scale, it feels it at some much larger scale. Okay, and what you can think is that in the short range effective regime, the effect of applying this cutoff is very similar to the effect of just reducing beta. Right? They have whereas in the long range effective regime, these are somehow totally different operations. Okay? And finally, as you will have come to expect, there is some logarithmic correction to this at the boundary case. Okay? So again, this is one of the things we compute in both of these two regimes. Okay? So, okay. So again, this shows you this a very concrete manifestation of this transition between being effectively long range, effectively short range at alpha equals 2. Okay. Okay. So what about the low-dimensional regime? And again, you should think of this radius of gyration as one version of the correlation length, i.e. it's the scale at which you begin to realize that you're not really critical. So in this case, beta is beta c, but the cutoff makes you subcritical. So we saw, at least in the high-dimensional case, that we can understand what it means to be long-range effective. Well, it means that the radius of gyration, the correlation length that you get when you impose the cutoff on scale r, is of order r. Okay? So the way that we will understand the low-dimensional case is essentially by just assuming that that's true. We'll just define that's what it means to be to have this long-range effectiveness. Okay. So let's say that the model is. So I'll define this property CL, which I call the correlation length condition for long edge relevance. Okay. Now you could define a version of this using something like the radius of gyration. One of the annoying things about the paper as it stands is the exact condition I use for this is quite ugly. So you can replace it with some stronger conditions, which are maybe less ugly and which maybe I should just do. But morally, it says that the correlation length as a function of the cutoff is big O of R. Okay? Now, the precise definition is that if you look under this under the cutoff measure of the Pth moments of the cluster at the origin, that it's of the same order as if you restrict to a large ball, a ball that's some large constant multiple of the scale where you did cut off the same power. And I need this for technical reasons for the first 4 moments. Okay, so one theorem, by the way, is that CL holds for alpha less than 1. Okay? It also holds when D is at least 3 alpha and alpha less than 2. So these regimes we were already talking about, the high dimensional and critical dimension, this condition does indeed hold exactly when it should, i.e. when the model is really long range. Okay? And this is essentially a corollary of these earlier results that I mentioned about the 2-point function, but it's not an obvious, maybe a corollary is a bit strong actually. It needs a few pages of proof, but it's closely related to that. Okay? So the theorem is that if D is less than 3 alpha and CL holds, so you should think of this as saying, if you're in this regime, and again, we're avoiding a discussion of like what the boundary of this regime is, whether it's connected. I mean, it could even depend on the choice of norm or whatever, right? And there's certainly no obvious monotonicity in alpha. But if you just assume that you're in the long-range relevant low-dimensional regime, then first of all, you do indeed get that the SAC prediction holds in a spatially averaged sense. And the volume tail is what it should be. And, again, as with all of these things, I've written down a couple of the kind of main takeaways, but it really, you get quite a comprehensive picture of what's going on geometrically. You can think that you actually get some precise versions of these hyperscaling relations. So, for example, I was telling you before about in the low-dimensional regime, for example, the best way to be in a large cluster is to be in the typical large cluster on an appropriately chosen scale. And indeed, you can really prove things like that, that really is the dominant strategy, and any other way of getting a large cluster will be less likely, things like that. Okay. Good. So an interesting thing here is that, this is still based on a similar idea of analysis, so using these cutoff measures and so on. But it somehow uses the way it works is you kind of say, if this isn't true, then that actually forces all the mean field behavior to hold. And then you can do all the same analysis you did in the high dimensional case, and in the end you get things that you just know are nonsensical. So it's sort of, in some sense, the low dimensional case still turns on the high dimensional analysis in an interesting way. And I'll hopefully be able to say much more about that later. Okay. Now, one thing you'll notice is that in contrast to the high dimensional case where we got very precise first order asymptotics and so on, here we're just getting up to constants estimates, right, which is what this symbol meant. And this is reflective in part of the fact that we really don't know what the scaling limits of these things are, right?
If you had a constant asymptotic, would you get?
Well, you might get the scaling limit of the volume tail or something. I'm not sure. It wouldn't really work like that. I mean, you can go from the scaling limit of the volume with the cutoff to a first order thing. I'm not sure about the other way round.
Do you have a conjectural scaling limit?
No. Yeah, I don't know. I mean, maybe just for the volume distribution, there might be a nice thing. I mean, it might even be one of these chi-squared with a different number of degrees of freedom or something. That's very speculative, though. I have no reason to believe that that's what happens.
I just missed one point. This condition CL in this region, or is there any place where we know it's...
Yeah, alpha less than 1.
Alpha less than 1.
So you should think, this is where I should stress again that this drawing is not uniquely define the interpolation down to 0. So alpha less than 1 you should interpret as this region. Okay, there's this bit here, but that doesn't really exist. So yeah, so you should think that essentially there's this piece of this region where we can prove everything completely unconditionally. And there's this larger region where you just have to axiomatically characterize what it means to be in the region, and then you can analyze things.
So alpha less than 1 and d less than 3 alpha means that d is 1 or 2, right?
Yeah, indeed, yeah. So in particular, we now have a complete understanding of this critical behavior in the one-dimensional case. And in the two-dimensional case, we get this interval of non-mean field models where we can prove everything unconditionally. Okay. Okay. Maybe I'll just say one more thing about this. Actually, I'll leave it for later. So we can get a bit closer than this towards understanding something about the scaling limit. which is not to say that we really can prove anything about there being a scaling limit, but we can in fact understand not just the 2-point function, but at least in this regime alpha less than 1, where we can get pointwise estimates on the 2-point function, we can actually get pointwise estimates on all the k-point functions and express what they are to 0th order, if you like, so order estimates on all the k-point functions. And one really interesting thing is that this quantity that we prove the k-point function is of the same order as is Mobius invariant. So I think that's really interesting. I mean, of course, being equivalent to a Mobius invariant function up to constants, it's unclear how powerful a thing that is. And of course, all our models we define with an arbitrary norm. So if you use the L1 norm or something, they're just not going to be rotationally invariant, most likely in the long-range relevant regime, because the Levy process limit remembers the fact that you use the L1 norm, at least in the high-dimensional case where you get the Levy process. So there's a sense in which you could be rotationally invariant up to constants without actually being rotationally invariant. And similarly here, we're going to get Mobius invariance up to constants, which I think is very interesting, but it's unclear where it's going to lead afterwards. But I'll say more about that later in the week.
The length of this Mobius invariance, it holds if you take the L2 norm, right? If your J had some norm L1 built in, you will be Mobius invariant.
If your
norm J,
is the L2 norm.
If it's the L1 norm.
Oh yeah.
Don't expect.
That's what I was just saying. Yeah. It's true up to constant still, regardless, but it's unclear what that means exactly. And of course, the other thing is, what we show is it's equivalent to some specific Mobius. The k-point function is equivalent to some specific Mobius invariant function up to constants, but there are many other Mobius invariant functions which coincide with that one up to constants. So it's in fact, the one that I'll write down, it seems pretty obviously not the correct one because it's all this it's not differentiable and so on. I mean, but anyway, we'll come back to that later. Okay. Maybe it's a good time to take a short break, and then afterwards I will sketch some of the proof in the high-dimensional case, which in some sense is much easier than everything that came before. And the interesting thing about this case D bigger than 3 alpha, it doesn't use any of the previous results that we proved on the 2-point function or anything. It's completely from scratch. And in fact, the method works exactly the same for self-voiding walk and Ising and lattice trees and so on. It's really very general and quite easy, powerful method, which I'll tell you about after we take a breather. Okay. So I'm sure you're all itching for some proofs, right? I think I've been holding back the whole series of lectures so far. And as I said, I think one of the really nice things about the high-dimensional case, at least, is that the proofs are very nice, particularly just for the volume tail. When you get into the scaling limits, the proofs are actually similar, but they're just combinatorially much more complicated. But we'll see in the volume tail that I think that it's really elegant and again fairly easy and generalizable method. Okay, so I'll say, maybe later in the week I'll tell you a bit about the critical dimension. The critical dimension is technically much harder, but the basic idea is very similar actually. So let's assume D is bigger than 3 alpha. Okay. So everything is done by differentiating the quantities we're interested in with this cutoff parameter R with respect to R, and then trying to analyze the derivatives. Okay, so let's start by looking at the first moment of the cluster at the origin. Okay? So we can begin by just writing down an exact formula for the derivative. Okay? And this is going to come from Russo's formula, which I talked about on Friday, and it's, generally for derivatives in percolation, you can write them in terms of pivotal edges. And, here we're doing something slightly different, which is that we're changing the truncation, but we sort of set up the way we do the truncation precisely to make these derivative formulas look nice. And so I won't tell you exactly the details of how we get to this precise thing, but let me just write down the thing. In fact, it's going to be convenient to do some of our analysis for now for general beta, and then we'll mostly specialize to beta C, but in fact, for this first proof, we need to consider subcritical beta, actually. Okay. So, the derivative is given by beta times, in general, the derivative of j. Okay, so for the level of generality I work in my paper, I just need to assume that this satisfies some asymptotic formula, but for us, let's just assume it's exactly r to the minus d minus alpha minus 1. Okay, and actually, there's one additional normalization convention that I'm going to make, which actually I should have already mentioned when I was talking about this moment formula, because it affects the constants, is that we're going to assume that our norm that we define the kernel with respect to has unit ball of unit measure. If you didn't do this, you would just get a lot of factors of this constant at the volume of the ball everywhere. So let's just get rid of that. Okay. So this is just coming from the amount that you're changing the probability that an edge is present. But of course, you only change the probability of edges of length at most r, right? And what does this derivative look like? Well, you can think I have the origin, I have some edge which is going to open up here into a distinct cluster, and I'm summing over the number of other points, the size of this cluster, i.e. the number of points that I add to my cluster if I merge these, where this distance is at most r. Okay, where I'm summing over x, y, and z, if you like. Okay, now, as I mentioned before, when you have these kind of sums over pictures like this, you can always, where you have one vertex fixed to be the origin and everything else being summed over, you can always change which vertex is fixed to be the origin without changing the value of the sum. Okay, so it's convenience here to make the origin this point and then sum over this point x. Okay, so in other words, you get, just beta this term, times the sum over y, now in just the ball of radius r around the origin, which I'll denote by br. And by the way, this ensures that br has volume asymptotic to r to the d. And the error here is small by a power of r. So I'm going to cheat slightly and just ignore the fact that there's an error here and just say, let's suppose there are exactly r to the d points in the ball, just to slightly simplify the analysis. Okay, and what do we get? We get the size of the cluster at the origin, k, times the size of the cluster of y, k sub y, times the indicator that they are in distinct clusters. Okay, this is just an exact formula for the derivative coming from Russo's formula after some manipulations. Okay. Now, how do we understand what's going on in the mean field regime? Well, the point is that most of the points in the ball, y is far from the origin. Okay, and in the high-dimensional regime, what should happen if you take these two clusters that are far away from each other? They should behave basically like they're independent, up to some correction. Okay, So what we would like to be true is that this derivative is asymptotic to what you would get if these two clusters were just independent, which is beta times r. Well, the r to the minus d cancels with the sum over the ball, which has r to the d points. So I would like to get this. Okay? And I think this point is really something where you see there's a major advantage to doing things this way, where you have the cutoff and so on, versus just differentiating with respect to beta and looking at what happens as you approach beta c. Because again, when you do that, you're going to be summing you can think it's similar to what would happen in the nearest neighbor case. Most of the derivative is coming from y close to the origin. And therefore, even in the high dimensional case, they're never going to be exactly asymptotically independent. You'll get some complicated constant here that encodes how these two clusters close to each other, they're not exactly independent, even in the beta goes to beta c limit. There's some constant factor encoding how they interact with each other microscopically. Okay? And if you do the lace expansion, part of what you're doing, if you like, is computing those complicated constants via some kind of series expansion. Okay? But here, when we do the cutoff and we remove it, we just get simple, explicit constant. I mean, we get a beta c, if you like, which is actually inexplicit and complicated, but it doesn't really matter. It's just beta c. Okay? Of course, that doesn't really matter that much for the analysis, but the fact that you get something simple just suggests things are going to be easier to prove as well. And of course, you can imagine it's easier to prove things are asymptotically independent than that they converge to some bounded dependence with a precise constant and so on in the limit. Okay. So basically what we want to do is we want to prove that this holds. Okay? Now, the first thing to notice is that if I do have this asymptotic relationship, so let's say I just have, just thinking about this abstractly, if I have a differentiable function and it's asymptotic to, let's say beta, suppose I have this like ODE, but it's only a first order asymptotic ODE. Okay. Then, in fact, if f of r tends to infinity, as r tends to infinity, but it's also finite, it blows up at infinity, but not before. This actually forces, in this case, that f is asymptotic to alpha over beta times r to the alpha. Okay? And why is this true? Well, it's just a calculus thing. You can check. You say, okay, look at 1 over f. Okay, what's the derivative of that? It's minus f prime over f squared. And you see the two f squareds cancel, so it's asymptotic to beta r to the minus alpha minus 1. And then you can just integrate both sides. You get an asymptotic formula for 1 over f, and then you invert. Okay, so one thing we'll see throughout this analysis is that we often want to understand these kind of first-order asymptotic ODEs. And these different kinds of first-order asymptotic ODEs have rather different properties in that, a basic question you can ask is a solution to the first-order ODE a first-order equivalent to a solution to the actual ODE, right? And in this case, that does happen, but it doesn't always happen. Moreover, you can see this analysis is very robust in that if you just knew, for example, that this was equal to this plus or minus something bounded but small, then you would also get that by the same analysis that f is equal to this up to some small constant multiples. Right? They don't have to go to 0. They just have to be, I guess, just bounded away from 1 or something. Okay. And it's really this fact that we get these good stability properties for this ODE is very important for the analysis we're about to do. Okay. So, So what I'm going to do is to just write our exact derivative identity as, well, what we want it to be times a 1 minus error term, right? So what we want this to be is beta r to the minus alpha minus 1 times the square of this. And I'm just going to write this as 1 minus an error term. Okay? And of course I can do that. I don't yet know this error term is actually small. Okay, and okay, but I want to give some bounds on this error term. Okay, so the first thing to notice is that the error is non-negative. I mean, I wrote it as a negative number there, but it's non-negative. And why is that? Well, if you like, this is just a BK inequality. Right? It's similar to this thing where we said that, the derivative with respect to P of the susceptibility is at most susceptibility squared. It's just, I form this first cluster, I try to open an edge and then explore the second cluster, and I just have less graph to work with because I already revealed a bunch of closed edges in the first part. That's all this is. Okay, so the error is non-negative. So what about a matching, not a matching upper bound, that would be great. What about an upper bound? So what I'll do is I'll say, well, let's take this expectation that we have. Okay, and I want to write this indicator as 1 minus the other indicator. Okay, which of course I'm allowed to do. Okay, now if I look at this first term, this is larger than, for each y, it's larger than the square by Harris FKG. Right, this is for each fixed y, it's larger than this, so the sum is at least BR times that. Right, that's just because I have two clusters and the size of the clusters are increasing events. That's it. Okay. Now what about this last term? So what I get is that this error is bounded by the contribution from this term, which, of course, if I'm summing over y in the ball on the indicator that they're connected, that's just the same as summing over the intersection of my cluster with the ball. And I get the square of the cluster at the origin, because k and ky are the same, times the number of y for which this indicator holds. And I wrote my error in this multiplicative notation, so I have to divide by the leading order term. So I get the volume at the ball times the square of the first moment. Okay? All right. So, you know, for some things like at the critical dimension and so on, the fact that you're restricting to a ball here is important, but for the analysis we're doing now, it's not. We're just going to bound this above by the ratio of the third moment to the volume at the ball times the square at the first moment. Okay, and we remember the tree graph inequality, that this third moment here is bounded by 3 times the fifth power at the first moment. Okay, and so what we get, just using the tree graph bound and then cancelling the powers, we get 3 times the cube of the first moment divided by the volume of the ball. Okay? Let's see if I can extract this. So of course, you know, as of yet, I don't know anything still, right? I mean, I bounded my error in terms of one of the other quantities, but, you know, it's often the case with percolation that proving your first estimate is the hardest thing to do, because you start off not really knowing anything about the critical behavior, and you have to start somewhere, right? And then once you have like a foothold, you can start proving more and more properties, but we're still at this stage of proving our first estimate. Okay, but the key thing that's going to make this work is that, well, what we expect is that at criticality, this first moment, well, we know if the error goes to 0, then we can solve the ODE and with the asymptotic ODE, and we should get this, right? So in particular, the numerator here should be like r to the 3 alpha, and the denominator like r to d, and we assume that d is bigger than 3 alpha. Okay, so we see, you know, if we were allowed to argue circularly, which we almost will be able to, as we'll see shortly, you know, if we knew that the asymptotic estimate we wanted to hold was true, then the error would go to 0, and therefore the asymptotic estimate that we wanted to hold would hold. Okay? Now, of course, that's not terribly useful, but the key thing is that if you have the correct behavior, it actually makes this really small. Like, you know, small by a power, it gives you a lot of room. So you don't really need actually the correct behavior here to already ensure that the error is small. And actually more accurate for the argument, if you know that this has the correct order on some large scale R, then using monotonicity, you can analyze the ODE even at much smaller scales. The information at the larger scale is already going to suffice to make the error small. And so we can kind of pull in the information from infinity. And that might sound a bit mysterious, but it's actually a very simple argument. So what we'll do is we'll say, suppose beta is less than beta c. Okay? So I can define R naught of beta to be, let's say, the supremal value of R, such that this quantity is more than double what it should be at criticality. This 2 is completely inconsequential. You could use any constant here. In fact, let's use beta. Okay? Now, I know, you know, by the sharpness of the phase transition, that, which I might prove tomorrow, actually, because it's relevant for the 2-point function things, but I know by sharpness of the phase transition that this, without any cutoff, this is a finite number, right, if beta is less than beta c. Okay? So in particular, this is finite. This R0 is finite when beta is less than beta c. Okay? Now, to conclude the proof, what we need to show is that in fact R0 is uniformly bounded. Right? It does not blow up as beta approaches beta c. If I can show that, then I'm actually done. Right? Because I'll get that the estimate the other way around holds for all r bigger than some constant at beta c. That ensures that the error goes to 0, and therefore I can analyze the ODE a second time. Okay, so what is the idea? So there's a lot of like annoying constant management in this proof if you do it properly, so I don't want to do it quite that properly. But what's the idea? Well, let's say if r is at least R0, right, then, well, this error is bounded by, okay, there's some constant r to the 3 alpha over r to the d, which is, let's say, less than 1 over 100 if r is also bigger than some other constant. Okay? So in particular, if R0 is larger than some constant, then you can analyze the ODE and you'll get the correct asymptotics of the solution above this thing. But the thing is actually, what if R is less than R0? Well, I can bound the error. This numerator is monotone in R, right? So I can just bound the numerator by the value at R0. Okay. So I get, some constant times R0 to the 3 alpha r to d. Okay? Now, the point is that d is strictly larger than 3 alpha. Okay? So what this means is that there exists a constant so that if r is smaller than R0, but bigger than R0 to the 1 minus epsilon, let's say times some constant, again, just to be careful, this also implies that the error is small. Let's say smaller than 1 over 100. Okay? So what this means is either way, if I look at this regime R0 to the 1 minus epsilon, if I look at the max of this or something, if R is bigger than this, then this ensures that the error is small. Okay? But we saw that if you just have a small error here, that suffices to analyze the ODE, and we just analyze it from the scale R, we get that the susceptibility, here we're doing the inequality version because beta is less than beta c, so it actually doesn't blow up as you approach criticality, but that's fine. You get, let's say, 1 plus 1 over 10, where this is a made-up constant, of course, but it's just some small number, times the asymptotics that you would get if the error actually went to 0. Okay? But of course, this is smaller than 2. So R must actually be larger than R0. Okay, so in other words, we get that R0 satisfies an inequality of this form for some positive epsilon and finite c, where the key point is this c. Okay, this is all these constants. I wasn't really telling you how to compute properly, but don't worry about it. This doesn't depend on, it doesn't blow up as beta goes to beta c. So you can just rearrange this inequality and you get this. Okay, so this shows that it's not blowing up as you approach beta c, and therefore, even at criticality, the bound the other way around is eventually satisfied. Okay, that means the error goes to 0, and then you can get actually the correct first order asymptotics. Okay, So you see, the only percolation things we used here were, first of all, Russo's formula, just to write down the geometric expression for the derivative. And then we used BK to bound the error in one direction, and we used FKG to bound this term. And then we used the tree graph inequality to bound this term. So any model where you have some appropriate analogs of those things, and sometimes the BK inequality can be used in kind of heavy ways that's difficult to mimic for other models, but this is not one of those times. We could have just phrased that in terms of an exploration argument. And so in fact, if this basic form of the argument, where so far we've just determined a first moment, you can run again for a large array of other models. It's essentially the same class of models for which the lace expansion has been applied to, I'd say, like Ising, self-weighting walk, lattice trees, percolation, and so on. Okay. Good. I guess I'm out of time, so I'll stop there for today, and I'll tell you something about the higher moments next time.
Are there questions?
So just to make sure, you said for Ising model you would have the equivalent proof for long range.
Yeah, you have to do it with the random current representation. I should say I'm working on that with Diederik van Engelenburg. Not terribly actively at the moment, but he came to visit me a while ago, and we worked through everything on the board, and it was clear that it worked. As always with these things, once you prove something, you're ambitious to prove something more difficult. So I think there it's very appealing to try to do the critical dimensional case. And one thing is that the really hard work for me in the percolation critical dimensional case is proving basically that this error goes to zero. This is much, much harder to do in the critical dimensional case. Once you know that the errors go to zero, you're kind of good. You're just doing calculations at that point. And this is a kind of marginal triviality type statement. And for the Ising model, marginal triviality is already known. So it was done for four-dimensional nearest neighbor by Eisenman and Dimno-Kapan. And then for the long-range models by Roman and Panis. So in that case, it's already known. So hopefully that will save. Whether their statement is exactly the one we need is not clear at this point, but it should hopefully save us a lot of pain.
Because at the critical point, you don't have the rule between D and 3 alpha.
Yeah, exactly. So actually one really...
The constants now, they probably start to...
Yeah, I mean, the proof is just completely different, actually, of this, that the error goes to zero. One really funny thing, though, which I find quite frustrating, actually. So suppose you slightly changed your model at the critical dimension, so that instead of working with... we were working with this kernel, and this is d over 3, right, for the critical dimension. Suppose that you make this slightly heavier by any divergent function. So suppose you times this by like the inverse Ackermann, for example. Just to stress the point. Then this proof works. And of course, whatever ridiculously slowly growing function you put here will appear all over the place in the remainder of the analysis. But it's some very slowly growing function, so it won't change the power of the logs, for example. And then this proof just works. If you really want to get exactly this kernel with no divergence, then you have to work very, very hard to get it to work. And if you want to do any kernel, just if you divide it by the inverse Ackermann function here, then I don't know how to do it. So it's a funny feature of the method somehow.
Okay, so if there are no other questions, let's thank Tom again.
Yes.